Okay, let's make carbon-carbon bonds. So we can also take benzene and alkylate. So for example, to make benzene into ethylbenzene. The problem with this is that because of the reduced reactivity of benzene, because of that aromatic stabilization energy, it won't do SN2 reactions readily. Normally we make these new carbon-carbon bonds by displacement of a leaving group with some kind of nucleophile. This just isn't a good enough nucleophile to do that yet. So we'd like to react it with an alkyl halide, right? That's normally how we do it, but it won't react with an alkyl halide. The alkyl halide is electrophilic, but it's not very electrophilic. The carbon is not great. So what do you imagine we might do to make this a better electron bond? Organic chemistry, that's smart. So we try to do the same shit we did last time and hope it works. And what we did last time was we got the chlorine to react with the Lewis acid and thus generate a more polar bond. So we're going to try the same thing and it's going to work. So you're going to attack the aluminum. Generate a tetrahedral aluminum atom with maybe a charge on it. And the tetrahedral aluminum with 4 chlorines on it is also a stable complex ion. So this is now a good enough electrophile to react with the benzene ring. We're not actually going to break that bond because the primary carbocation is not stable. That bond is going to break in the process of being attacked by the benzene ring. Form the carbon-carbon bond, take this pair of electrons out. We're going to make the tetrachloro aluminate ion. We don't have to specify the oxidation state of aluminum in that one because it's always +3. So tetrachloro aluminate. And then we got to take a hydrogen off, right? This one, not that one, never that one. Take the one off the sp3 hybridized carbon, lose the base. The bottom of that group closest to hydrogen. So we're going to generate HCl. Yes. And benzene and regenerate AlCO. So it's catalytic in aluminum chloride. So just ethylbenzene or an alkyl chloride and aluminum chloride. This reaction is called Friedel Crafts alkylation. And it's a terrible reaction. It really sucks. There's two reasons it sucks. One is it's not generally applicable to all alkyl halides. If we were to try to do the Friedel Crafts alkylation, with isobutyl chloride or 2-methyl 1-propyl chloride, or 1-chloro-2-methyl propane, we would actually not get the product that we expect. Because we aggregate it, but now aluminum would think about taking that chlorine and leaving, and this hydride would help it by moving to generate not the isobutyl cation that we wanted, but the tertiary butyl cation, which would be fine if what we wanted was tertiary butyl bromide, or tertiary butyl benzene, rather. But it would not be fine if what we wanted was isobutyl benzene. So carbocation rearrangement can't be prevented because you can generate carbocations. And it's an even bigger problem if your chloride is secondary and next to a more substituted center. So it's limited. You can do it, but you can only do it with kind of situations like this where a hydride shift wouldn't matter. If you try to do it with chloropropane, you're going to get some propylbenzene, but you're also going to get some isopropylbenzene from this intramolecular, this concerted hydride shift. I didn't focus on hydride shifts in a concerted fashion last semester. Right? We just basically generated carbocation and then it shifted. For concerted hydride shifts like this, where you would generate a primary carbocation, and you're not going to do that, you have it in your normal circumstances. The other problem with the Friedel Crafts alkylation is this is more reactive than the parent. That's a problem, right? Because it means once we put the one alkyl group on there, that's more likely to react with the electrophile than the original one, so we get multiple alkylations. We can't solve that problem by limiting it to one equivalent, because as soon as you make the ethylbenzene, if it collides with the electrophile, is more likely to react with the benzene was in the first place. So we won't convert all of the benzene to ethylbenzene, and we will end up converting some of the ethylbenzene to diethylbenzene, maybe even triethylbenzene. Does it look like it would be easy to separate ethylbenzene from diethylbenzene? Is that something you'd like to have to try to do? Nah, that probably sucks, right? So you're somewhat limited. There are other ways of generating alkyl cations besides the Friedel Crafts reaction. And sometimes they're useful, and sometimes they're not. You can also use alkenes. And if you react alkenes with HF, fluoride is a shitty enough nucleophile that it will not compete, won't out-compete with benzene, so the benzene will react rather than with fluorine, and we can get an electrophilic aromatic substitution reaction. Right? So it's got to be HF, it can't be HCl, right? If you use HCl, you're just going to get TButyl chloride, HCl, you get TButyl bromide. But by using the non-nucleophilic halide ions, you can generate that. And you can also generate them from alcohols by reacting with CF3. Once you've generated that complex here, this falls off. You generate the carbocation, this isopropyl carbocation, and HOPF3. That's your base in the last step of the Friedel Crafts reaction to generate water as a product. So if you were to write that reaction as a note card, it would look like this. With the BF3 and the isopropanol, you generate this plus water. And that reaction works reasonably well. In this case, since no carbocation rearrangement is favored, but you still have the problem, the potential problem of over-alkylation. Makes sense, right? Lewis acid behaves very similarly to the Friedel Crafts. This is not a Friedel Crafts reaction. Friedel Crafts reactions are alkyl chlorides and aluminum chloride, but mechanistically it's similar. So you can alkylate benzene, but you worry about over-alkylation and then having to separate a complicated mixture. And if carbocation rearrangements are possible, you can't prevent them from occurring. If carbocation rearrangements are not possible, then it's fine. So how can we put an alkyl substituent on there and not have to worry about over-alkylation and not have to worry about rearrangement? It's another Friedel Crafts reaction. and Friedel Crafts acylate. Probably it comes as no surprise that if you can activate an alkyl chloride by treating it with a Lewis acid, you can probably activate an acyl chloride as well. Okay, so in this case, 2-methyl propanoyl chloride. This one's not catalytic. You have to use the full stoichiometric equivalent of aluminum chloride to make this reaction go. And the reason for that is that this oxygen will bind to aluminum chloride after the reaction is complete, form a complex. And that complex will only break off when you do your acidic workup. So when you treat this with acid, you'll protonate, and you'll end up with aluminum hydroxide and HCl. But until you've done that, that aluminum chloride is binding to that oxygen and preventing it from going back and reactivating another acyl chloride. Mechanistically, it's basically the same as halogenation or Friedel Crafts alkylation. It's the chlorine atom on the acyl chloride reacting with aluminum chloride. We're still going to generate the tetrachloroaluminate ion. I'm going to leave the other pairs off the other 3 chlorates since they don't matter. But in this case, because you have this oxygen present, tetrachloroaluminate can actually leave to generate acylium ion. And we saw ions like that in mass spec. That the acylium ion is a pretty good electrophile. It's got a resonance structure that puts a positive charge on the carbon. That's not a very favorable resonance structure, but it's there. So the acylium ion reacts with the benzene ring. Or the intermediate. Like that. And then the tetrachloroaluminate acts as the base again. Yanks that hydrogen off to form HCl. And the product. I'm taking the hydrogen off the sp3 hybridized carbon. And after acid workup, I keep saying acid workup, but I don't mean acid workup, I mean basic workup. Usually bicarbonate, or something like that. That's going to quench the HCl. We'll break that complex and generate the So that's Friedel Crafts acylation. Because this is electron withdrawing, this ring is actually less reactive than the parent. So you don't have to worry about double acylation. That acyl group isn't going to go any further. One of the nice things about the Friedel Crafts acylation is that alkyl groups and acyl groups can be interconverted. So once you make that acyl group, it is possible to convert that to the alkyl group, both forward and backwards. You already know two different ways of doing that. But there's a third way of doing that that is commonly used in aromatics and less commonly used for non-aromatic materials. And that's why what's called the Clemmensen reduction. Reduction uses zinc amalgam in the presence of HCl, and it will reduce a carbonyl group to a CH2. But you also know that you can do that with first making the dithiazide and then doing radionickel desulfurization. And you also know that you can do it with full picture. Hydrazine and base. Right, so those are other alternative ways of converting the acyl group to the alkyl group, reducing a CO to a CH2.
So is the zinc one on top one as well?
This one is called the Clemmensen reduction. That's one way to do that, and then these are the other two that you already know.
Okay, thank you.
So this is new. It could also be done with iron, just iron solid. And it's, you know, that was in the textbook as well. Similar, right? Zinc amalgam or iron will both do that in the presence of acid. You already know how to go the other way. Right? That reaction, you know, in theory, maybe. Oxidizing a CH2 next to a benzene ring, this is a benzene position, so it's reactive.
And then the two.
And that can be done with chromium 6 oxide. MnO2 oxidizes benzylic alcohols. This isn't an alcohol, this is CH2. Right? So you can convert back and forth, which means you can take a ring that's more reactive than benzene and convert it into a ring that's less reactive than benzene and vice versa. Very handy. You can also react an NO2 group and form an NH2 group. Using the same method, the Clemmensen reduction, we'll also convert an NH2 to an NO2. An NH2 and the modification will work as well. Right? The higher solid HCl and the catalytic hydrogenation with nickel. In this case, we don't have to convert it to a dithiazide first, just radionickel and hydrogen gas. We'll convert that, and you can go back the other way using a peroxy acid. That's handy because NO2 is inductive electron withdrawing and renders the ring less reactive, and NH2 is resonance electron donating and renders the ring more reactive. So we frequently want to convert an NO2 group to an NH2 group or back. And once you have that NH2 group, you convert that NH2 group into lots and lots of other things. These two reactions that I just talked about here are in section 16.5 of your text. And the conversion of the NH2 group into lots and lots of other things. So we can convert that NH2 group to an OH group, and we can convert that NH2 group to a chloride, and we can convert that NH2 group to a bromide, and we can convert that NH2 group to a nitrile, and these are hiding in section 22. You can also remove it completely. Just take it off there, convert it to a hydrogen, and you can convert it to an iodide. All of these reactions are based on the initial reaction of the NH2 group. NO2 in presence of HCl. Usually the HNO2 is introduced as NaNO2 because HNO2 is an unstable acid. So it's nitrous acid. And when you treat NaNO2 with HCl, what you form is nitrous acid. Nitrous acid reacts with additional acid to form water, and the nitrosyl cation. That nitrosyl cation will react with benzene ring to put a nitroso group on the benzene ring, but that nitrosyl cation will also react with the amine to form a diazotization salt. And this diazonium salt reacts with water to form an OH group. It reacts with cuprous chloride or cuprous bromide or cuprous cyanide. Right? So the first step is the same. It's always NaNO2 and HCl and water. If you don't put anything else in there, you get the phenol. But if you put a cuprous salt, these are copper 1 salts. You get what's called the Sandmeyer reaction. Right? And it can be copper 1 chloride, it can be copper 1 bromide, it can be copper 1 cyanide. These bottom reactions are known as the Sandmeyer reaction. That's in section 2210. If instead of reacting it with HCl, you react it with HI, then you get the iodide. And if after reacting it with NaNO2 and HCl and water, you then react it with H3PO2, hypophosphorus acid. That's a reducing acid. reduce that diazonium salt to the hydrogen. You can imagine nitrogen gas leaving, right? They actually generate a carbocation where there's an sp2 hybrid orbital there that has no whether this is an actual discrete intermediate or whether the diazonium salt reacts directly with the nucleophile at this position is questionable. But it basically acts like a benzene cation, and then it gets attacked by either water or chloride ion or bromide ion or cyanide ion or iodine ion or whatever is present when hypophosphorus acid. So the ability to convert an NH2 group into a diazonium salt and from the diazonium salt into just about anything else is very handy. It's easy to nitrate benzene, it's easy to reduce nitrobenzene to aminobenzene, aka aniline, and it's easy to convert it to lots of other shit. So section 22.5, sorry, section 22.10, which is where this one's actually 22-4, but it's the same general idea. And section 16.5 is where you have that nitro to amino, amino to nitro, and then acyl and alkyls. So lots of reactions. You can make note cards for all of these. You can learn all these reactions. You've got a whole week since we don't have class on Tuesday. I'll post this video up there so you can watch it again slower. And then we'll talk about directing effects